So this is the second part of a two-part video series, and we're calculating the pH of sodium nitrite. And we discovered in the last video that sodium nitrite is a basic compound. In fact, we only really have to look at the nitrite ion there. The sodium ion, since it comes from a strong base, is going to be neutral. The nitrite ion comes from a weak acid, therefore it's going to be basic. And what we did in the last video is we had a 0.1 molar solution of sodium nitrite, which is really just a 0.1 molar solution of the nitrite ion, and we were trying to find the pH. And what stymied us is that we didn't know the value of Kb. However, it turns out that we can show that Ka and Kb for conjugate acids and bases are always equal to Kw. So we can calculate Kb if we know Ka and we know the value of Kw. So let's go ahead and look up Ka for the conjugate acid. So first off, what is the conjugate acid? Well, if that's the base, the conjugate acid is where I just give it one more proton. So it would be HNO2. And let's pull up a table. All right, so this table from our textbook gives Ka values for some monoprotic acid. So here is nitrous acid at the top, so otherwise known as HONO, and HNO2 has a Ka of 4.6 times 10 to the minus 4. So that means that this conjugate base here, the NO2 minus, has a Kb that we can calculate for that. So let's go ahead and do that. So Kb then for the nitrite ion is equal to Kw, so at 25 degrees C, that is 1 times 10 to the minus 14, over Ka for the nitrous acid. And we already saw that that is 4.6 times 10 to the minus 4. And so we plug that in, we'll get Kb for our nitrite ion. And I get 2.2 times 10 to the minus 11. So it's very, very small, right? So it's not a very strong base at all. All right, now we are ready to calculate the pH of this solution. So let's go to another slide and crank through this problem. Okay, so now we're ready to do it. So I'm going to replicate the ice chart from before, and I'm just going to go ahead and speed this up like 4 or 5 times because we've already done this problem already. So I'm just going to write it out. So here we go. All right, so back to single speed now. So Kb we already calculated from Ka and Kw. So we saw it was equal to 2.2 times 10 to the minus 11. And the bottom of our ice chart gives us x and x for the two top terms there. So that's x squared. And the bottom term is 0.1 minus x. And we're going to go ahead and make the approximation that x is much smaller than 0.1, which allows us to write x squared over 0.1, because if x is much smaller than 0.1, we can take away a very small number from a large number, and we're essentially left with a very large number. Remember, we have to calculate the 5% rule. We have to check that x is smaller than 5% of 0.1 in order to fully validate this. All right, so we are solving for x, so we can say x squared is 0.1 times my Kb. So that's equal to 2.2 times 10 to the negative 12. All right, we don't want x squared, we want x, so that is just the square root of that mess. And, okay, I'm too lazy to write it in, so that is going to be 1.5 times 10 to the minus 6. Okay, so in terms of our 5% rule, 1.5 times 10 to the minus 6 is something like 0.0015% of this. So it's only going to go in 0.0015% dissociation. So our 5% rule is totally kosher here. All right, what do we want to do? We want to find the pH, and we don't have the H plus concentration, but we have the OH minus concentration, and that allows us to calculate the pOH. So the pOH is the negative log of the hydroxide concentration, and well, that's just equal to X, and that's just equal to 1.5 times 10 to the minus 6 molar. And so we can calculate the pOH, that is 5.82. Notice it's not the pH. The pH and the pOH, if you remember, add to 14 at room temperature. So all we have to do is subtract 14 and the pOH, and that gives us a pH of 8.18. Does that make sense? Well, the pH is above 7, so that's what we'd expect for a basic solution. So yeah, I suppose it makes sense. One other thing here, we assumed that the 10 to the minus 7 moles per liter of hydroxide in pure water could be ignored. And this is probably our first situation where we're probably introducing a little bit of error here, because if you add 1 times 10 to the minus 7 to 1.5 times 10 to the minus 6, you get 1.6 times 10 to the minus 6. So we're definitely in dicey territory here, and certainly if this was any smaller, we'd have to really worry about this. But that's actually a story for another day. In fact, that's a story normally for analytical chemistry. So we'll punt this question to a analytical chemistry course, and we'll just pretend we didn't see it. Is that okay with you?